Okay, there was one question in the break about the concept of field. Okay, we are talking about electric field, or in Turkish we have elektrik alan. Okay, the concept of field here has nothing to do with the concept of field in, let's say, strawberry fields. They are not related. And the alan over here, it is also the same word for area. It has nothing to do with area, it has nothing to do with strawberry fields. Now, the mathematical concept of this field, well, the mathematical, we don't even say the electric field, we call it a vector field. A vector field, it is just like an ordinary function in the sense that for it, it's a function that assigns a vector to every point in space. Well, you can say that this concept of field is similar to a strawberry field in the sense that also in the strawberry field, the hope is that you will find a strawberry at every point in the field. So this is the definition of a field in the mathematical sense. It is not area, it's not something two-dimensional. It is just a function that assigns a vector to every point in space. So that's what we are also saying. If you have some charge over here, at every point in space there's an electric field, which is a vector. So that is why we call it an electric field. It assigns the electric field at that point. It assigns an electric vector at every point. Other questions? It does exist in English. I mean, it's a place where you go and you can pick up some strawberries and eat them. There's also a song. So what is the question? Around the extended object. So, okay. So your friend is asking, what is the electric field of an extended charge distribution, right? So you have a, let's say you have a ring which carries a total charge of, let's call it Q, distributed uniformly, for example, right? Is this your question? Now let's calculate the electric field of this configuration. Now, the charge is distributed uniformly. Well, our formulas that we had used until now are valid only for point charges. This is definitely not a point charge, but we already know the trick, what to do. We can just divide this into very small pieces. Each will be almost a point charge, and then we know how to express the field created by that point charge and sum all the charges. That's what we will do. So we will just divide it into small bits. Each one will have, let's say, a length. Let's call this dl. So the charge over there, well, the charge is uniformly distributed, so the charge per unit length is q over 2 pi r, r being the radius. If this piece have a length dl, so the charge of that segment is just multiplied by dl. Now, if you want to calculate the electric field at an arbitrary point, it does get a bit complicated. But let us just try to calculate the electric field on this line. It is a line that goes through the center of the ring and perpendicular to the plane of the ring. And we are at this point. And that point, let's say it's at a distance d from the center of the ring. So what will be the electric field there? Now let's just take one segment. Now just to show it easier, let's also consider this segment over there. It will create an electric field in this direction. This is dE. And let's say this is the angle theta. Now, just for demonstration purposes, I am assuming that Q is larger than 0, but the final result will still be valid even if charge is less than 0. I mean, if the charge is less than 0, the electric field here will not be pointing in that direction, but it will be pointing in the opposite direction. That will be the only difference. Well, this point has, this segment over here has the diametrically opposite segment over there. This one, which will also create an electric field. And it will be, let's call it dE prime. Now, what can you say about the magnitudes? I'm assuming that I'm dividing my ring at segments of equal length. So what can you say about the magnitudes? They will be equal. Remember, because, and all of them will be equal to 1 over 4 pi epsilon 0. Let's call this distance L dq over L squared. For all these segments, L will be the same length because since I'm on this line, L will have the same length. For every segment, L is the same. Since I'm assuming that each one of the segments have the same length, dL, dq is the same for each one of the segments. dq is the same, L is the same. So the magnitude of the electric field created by each one of these segments at this point, they will be equal. Now I have this point. This is dE. This is dE prime. Now this is dE prime. With the horizontal, they both make the same angle, theta. So let's see, dE as a vector. How can we write dE? X and Y. It is its magnitude times cosine theta in the x direction plus dE sine theta in the y direction minus. Because you see, dE is going below the x-axis, so it's in the minus y direction. Now dE prime will be more or less the same thing, dE cosine theta in the x direction plus dE sine theta in the y direction. But dE prime, their magnitude are the same. So I can use dE. They have the same magnitude. Now, when I sum these two, you see the y components, they just cancel. I am only left with an electric field in the x direction. Now, this is true for any such diametrically opposite points. So for any segment, there will be some diametrically opposite segment. And if I sum the electric fields created by these two segments, the y component will be cancelled. So I will, at the end of the calculation, when I sum the electric fields created by each one of these segments, I will end up having an electric field in the x direction only. So although this dE has a component in the y direction, I don't really need it, because I know that it will be cancelled eventually by some other contribution from some other segment. So it's enough for me to keep track of the contribution to the total electric field along the x direction. Well, to start with, I know that the total electric field will only have the x contribution, because any contribution in the y direction will be cancelled by another contribution in the y direction. They always come in opposite signs. Now this Ex, the contribution in the x direction will be nothing but the contributions along the x direction of each one of these segments. But we said that each segment, its magnitude is already given by 1 over 4 pi epsilon 0 dq over L squared. But of course, I'm taking into account only the x contribution, which is proportional to cosine theta. Cosine theta. This is the x component of this dE. Now, for each one of these segments, L is the same. Theta is the same. Theta is the same for each one of the segments. So theta is the same for each one of the terms in this sum. This sum is the sum over the contributions of each one of these very small segments. So since cosine theta is a constant, L is a constant, 1 over 4 pi epsilon 0 is a constant, what I am left with is 1 over 4 pi epsilon 0 cosine theta over L squared sum over dq. Well, this dq is the charge of one of the segments making my ring. I'm summing over all the segments, but that gives me the total charge of my ring, which I said was equal to q. 1 over 4 pi epsilon 0 cosine theta times q over L squared. Now, cosine theta is 1 over 4 pi epsilon 0 q. Now, cosine of this angle is nothing but d over L. And L is d squared plus r squared. So the electric field is q over 4 pi epsilon 0 d over d squared plus L squared to the 3/2 in the, let's say, d hat direction, in the x hat direction. This is the electric field on the line that goes through the center of my ring. Not at an arbitrary point, but only on the line. Now, the one question, does this answer make sense? I mean, whenever you obtain some result at the end of some mathematical manipulation, you should always ask yourself, does this answer make sense, at least in certain limits? For example, we can see that when d is equal to 0, the electric field is 0. Does it make sense? This is how we define the D. When D is equal to 0, I'm looking at the electric field right at this point, and the electric field is 0. Does it make sense? Your friend said yes. Yes or no? Now, our answer, well, let me draw it again here. So this is my ring. I'm looking at the electric field on this line, let's say at this point, which is at a distance d from the center of the ring. The ring has radius r. By the way, this is not L, this is R. Yes, they are the same thing. Yes. It is this D. No, here is the same equation. No, sorry. This dq is not equal to d times q. dq is a very small charge. Okay, bad notation. Now the question is this. This is the result that we obtain for the electric field. And we see that for the electric field at this point at a distance d from the center of the ring. If you look at this equation, when this d is equal to 0, electric field turns out to be 0 if this equation is correct. Does this result make sense? Now, when d is equal to 0, we are looking at the electric field right at this point. Does it make sense that it is 0 there? Yeah. So it makes sense. If I'm here, if this part segment creates an electric field pointing in this direction, this segment will create an electric field pointing in exactly the opposite direction. So all the electric field will be cancelled. So that makes sense. Now, what do you expect the electric field look like when d goes to infinity? D goes to infinity, meaning that d is much larger than r. Or when r goes to 0. Well, it will just behave like a point charge. If r is very small, then it's obvious that it behaves like a very small point. When d is very large, there is this ring, but you are so far away from the ring that it just looks like a point. So the final result should be very similar to an electric field of a point charge. So let's see if that is satisfied. Now, if r is very small, much smaller than d, then you can just neglect r compared to d squared over here. So this term will cancel. I have the d squared raised to the power 3/2, but that is d cubed. There is one d over there. They also cancel. So the electric field as d is much larger than r, it just becomes q over 4 pi epsilon 0, 1 over d squared in the exact direction. So this is also what we expect. Now, your friend's question, what does it look like? Well, since the electric field is just the electric field of a point charge at a faraway distance, the electric field lines should also look the same. So let's say this is my ring. Now, very far away, the electric field lines should be just radially outward. At the center, it should be 0, but that's mainly because the electric field lines should start at the rim of my ring, so they will be something like this. So let's see, this is just a two-dimensional cross-section. So they should start from here. It will look something similar to this one. Sure, but the ring is just very thin. We ignore the thickness of the ring. But if you don't ignore the thickness of the ring, it should be perpendicular to the surface. I think I have a simulation of how it looks like. I mean, on next Tuesday, I will show you the simulation, how the electric field lines look like of this ring. Other questions? Okay, take yourself, lie down. It will be horizontal. It's the same thing. I mean, laws of nature are invariant under rotations. So you can just rotate it. Either rotate the ring or rotate yourself. Let's do another example. So let's assume that we have a very thin flat sheet. Well, in principle, infinitely long. And the surface, so what we call the surface charge density is sigma. The surface charge density is nothing but the charge per unit surface area. Now, what will be the electric field created? Now, we are assuming an infinite flat sheet. Well, in reality, we never have this infinite flat sheets. But in physics, I mean, just like in the previous case. Now, we said that as d goes to infinity, the electric field behaves like this. The infinity just means that the d should be much, much larger than the r. In this problem, we say that there are two length scales. One is the size of the ring. The other one is the distance from the ring. So you can just compare those two things. You cannot say that a dimensionful object is very large. It just doesn't make sense. If something has a dimension, then you can only say that it is larger than some other object. Now, the same thing applies here. When we say infinitely large sheet, we are actually meaning a very large flat sheet, but what does it mean for a sheet to be large? Its size should be very large, but again, it has a something of that has the units. It just doesn't make sense to talk about an object having units to be large or small. You have to compare it with something else. And here we again look at this point above this sheet at a distance, let's say d. Now, let me not use the symbol d anymore. At a height L from the surface of the sheet. So the size of the sheet should be much, much larger than this L. Practically infinite. So what will be the electric field created by this very large flat sheet of surface charge density sigma? Well, this is again not a point charge. So we can do various things. We can just either divide it into point charges, just very small segments, calculate the electric field created by each one of these point charges and sum them up. That is one strategy. But now we already know another expression for the electric field. So if we have some ring, we know it's electric field, at least on the line that is connecting the ring, connecting the center of the ring to my point. Now, by the way, before we pass on, so this is what the field lines look like from very far away. If we are very close to the ring, this is my ring, this is how the electric field lines will look like. At the center, there's no field lines. So if the electric field line just goes just straight, will bend like this. Of course, just think of this ring as three-dimensional. I mean, I'm just cutting the ring into half. This is one side, this is the other side. Now back to this example. Now, I also know the example of a ring, how much electric field the ring creates. So I can just divide this infinite surface into very thin rings. No? Let's see. I imagine a very small ring like this. I can just imagine concentric rings that will make up the whole sheet. So if you just look at from the top, this is the point in which I would like to calculate the electric field. This is my surface charge density, infinite sigma. So I'm just imagining that I have this plane I can just form as a sum of these rings. When I sum all of these rings, I ended up having an infinite plane. Now, each one of these rings, let me take one of them. Now, it has a radius, let's say r. It has a thickness, let's say dr. What is the area of this ring? Of the ring. Okay, if you just open up this ring, it looks like a rectangle. The length is 2 pi r, the width is dr. So the charge of this ring is sigma times dA, because sigma is the charge per unit area. The area of the ring is dA, so the total charge is the charge per unit area times the total area. This is equal to 2 pi sigma r dr. This is for one ring, the charge of that ring. Now we already have, let's see, let's call this direction the z-axis, z direction. So we know that this ring creates an electric field in the z direction. And the electric field created by that ring is given by this expression. So let's say now, of course, since it has a very small charge, it will create a very small electric field. The charge of my ring, this was the charge of my ring in the previous example. Now the charge of my ring is 2 pi sigma r times dr divided by 4 pi epsilon 0. Now this d is the distance of my point where I would like to calculate the electric field from the center of the ring. Now in this problem, I just labeled it L. divided by L squared plus R squared. R was the radius of my ring, now I denote it by small r, to the 3/2, and it's in the z direction. This is the electric field created by one ring of radius r. Now the total electric field will be nothing but the sum of these. Of course, eventually I will assume that each one of these rings are infinitesimally thin, so I have to sum infinitely many of them. If I sum infinitely many of infinitesimally thin things, I will have an infinite sum of zeros, but that is nothing but what I call the integral. This is equal to the integral from 2 pi sigma r dr divided by 4 pi epsilon 0 L over L squared plus R squared raised to the 3/2 in the z direction. Well, the minimum possible value of R is 0. The maximum possible value of R, infinite. And then you need to evaluate this integral. And if you evaluate this integral, it just turns out to be sigma over 2 epsilon 0. And the evaluation of that integral I'm leaving to you as an exercise. Yes, and each one of these rings have an area dA. This is just one of the rings making my infinite sheet of charge density. Well, this dr is the thickness of each one of these rings, or you can say that it's the differences of the radius between two successive circles. Now, if this is my sheet, I'm just looking at it from the side. We had just shown that the electric field at this point is pointing upward, and it has a electric field is sigma over 2 epsilon 0 z. It's a uniform electric field. So if I want to draw the electric field lines, their density should be uniform. This is how the electric field lines will look like, because the magnitude of the electric field is just constant. It is independent of how far away I am from the ring, from the plane. Well, if I am at the lower half, then the electric field line will be just electric field will be minus sigma over 2 epsilon 0 z hat. It is pointing downward. Well, that also makes sense, because if this is, let's say, a positively charged sheet, if I put a positive charge over here, it will feel a downward force. If I put a positive charge over here, it will feel an upward force. And so it again has the same magnitude. So the density of the electric field lines are still the same. So this will be how the electric field lines will look like. Okay, there was one question about the continuity of the electric field lines. So one of your friends had asked whether the electric field lines are always, electric field is always continuous. Now here you see that the electric field is not continuous, because just above this sheet, the electric field is pointing in one direction. Just below that sheet, the electric field is pointing in the opposite direction. So that just tells me that the electric field is not a continuous in space. It has a discontinuity where I have some electric charge. So unless I have some electric charge somewhere, the electric field line will be continuous. But at the points where I have electric charge, I might have such discontinuities. You can say so. But the difference is there, I mean, for a point, we don't really call it a discontinuity. We call it a singularity. It diverges over there, so it doesn't really make too much sense to talk about the electric field there. But here, the electric field is everywhere finite. There is no divergence of the electric field, but it's just discontinuous. Okay, now, does it make sense that it is independent of our height? It doesn't change with distance. How come? I mean, for a point charge, we know that if we are going further away from this point charge, the electric field is getting reduced. Well, if you just imagine yourself on this surface, you have an infinite surface, you are just looking at the surface without anything else. How can you tell your distance from the surface? I mean, whenever you are talking about distances, you are always comparing something with something else, unless you are using your own, I mean, of course you can just compare your distance from the surface from your body, by just going there, but without going there, by just looking at the surface, how can you tell your distances? Now, I can tell that I'm further from my friend at the back than I'm from him, because when I look at him, he looks huge. When I look at your friend at the back, he looks very small. So just comparing the two, I can say that he's closer to me than him. Unless, of course, he's a giant and your friend over there is a dwarf. Other than that, I mean, if without such information, such something to compare, I cannot really tell how far away I am from. And the same thing holds for this infinite plane. I cannot really tell, or nothing can really tell how far away you are from the infinite plane. Whatever your distance is from the infinite plane, it will always look the same. So that's why the electric field turns out to be independent of your distance from the plane. Now, could we have guessed that the direction of the electric field should be perpendicular? I mean, of course, we did all these calculations, we calculated the integrals, and at the end, the electric field turned out to be perpendicular and uniform. Well, uniform we could say because, well, there's practically no length scale in our problem. So if we have one length, we have to compare it with some other length. But here we don't have that other length. So we could say that, okay, it doesn't change with distance from the sphere, from the plane, but could we have said that, why not having an electric field lines inclined in one direction? Why vertical? So this is my question. Okay, this is my infinite conducting sheet. Why not have electric field lines like this? The charge is static. It's not a conductor, so it doesn't have to be perpendicular just by using our previous arguments. In this electric field, again, the electric field is independent of your distance from the conducting sheet. But why can't we have this? Well, potential we don't know for this electric field. So your friend is saying that if I just look at this point over here, your friend is saying that for every point over here, there is another point on the symmetrically opposite side, so their horizontal components will cancel. I only have a vertical part. But I can say that not necessarily symmetric, but for every point here, I can take a segment that is twice as large on the other side at twice the distance. So for every small segment on one side, I will have a larger segment on the other side. For everyone, I will have another one. But it doesn't work. Why not? Okay, what do you mean by your friend is saying that since we have equal charges, the lines will be deformed. What do you mean by that? Okay, we are running out of time, so. Well, for an infinite side, you can say that for every point, for whichever point you choose, it will be at the center. But you can also say that for every point you choose, it will be off the center. Both are valid. Why choose that one? Okay, for you to think. Any last minute questions before we go? Okay, see you on Tuesday.